Hello and welcome to this online lecture about Bronsted Lowry acids and bases. Um, some scientists investigating the chemistry of acid and base reactions a long time ago, back in the early 1900s, 1920s, discovered that the Arrhenius definition really wasn't enough when it came to examining what's happening with different kinds of chemicals in acid-base reactions. And two of those scientists, Bronsted and Lowry, independently came up with a different definition for acids and bases that we now call the Bronsted-Lowry system or theory of acids and bases. So by the end of this video lecture, you should be able to look at a reaction, the equation for a reaction, and determine what in that reaction is an acid or a base according to the Bronsted-Lowry acid-base theory. So the way that this works is it's all based around protons. The Bronsted-Lowry theory is a theory about protons. And at this point, you should know that protons are the positively charged particles that we find inside of atoms. And you probably also will know that if you have one proton, you basically have a hydrogen ion, because hydrogen has one proton in its nucleus. And so if you just have that one proton without an electron around it, that's a hydrogen ion. So what that means then for the Bronsted-Lowry definition is that hydrogen and hydrogen ions are going to be crazy important. So we're always going to be wanting to look for hydrogen and what it's doing in a reaction. So according to their definition, you can consider something a Bronsted-Lowry acid. I'm just going to abbreviate BL. A Bronsted-Lowry acid if it gives away a proton. So we call them proton donors, gives it away. So proton donor. And then you can consider something a Bronsted-Lowry base when it accepts the proton that the acid gave away. So it's the proton acceptor. So really what this boils down to, it's not that difficult. You have to look at a reaction as it's occurring, and you have to ask yourself, is one of the reactants giving a proton to the other reactant? And if the answer to that question is yes, one of them is giving away a proton and the other one is taking it, the one that's giving the proton away, the proton donor, is the acid, and the one that's accepting the proton is the base. So let's just take a peek here at a simple reaction and see if we can figure this out. So you don't have to have water for a Bronsted-Lowry acid-base reaction to be occurring, but the very first reaction we're going to look at is just a really simple one where we can get these definitions nailed down. So we're going to look at what happens when you put HCl, hydrogen chloride, in some water. So basically what happens is that the hydrogen chloride, the HCl, breaks apart into the two ions that it's made out of, the hydrogen ion and the chloride ion. And we talked before about the fact that a hydrogen ion is basically just a proton. So we already see in this reaction that we have a proton here, and the proton's coming from the hydrogen chloride. And so what happens is that proton can hook up with a water molecule. And that's exactly what we see. The proton comes over here and joins this water molecule. So now instead of having two hydrogens, the water has three. So it becomes H3O. And we know this compound is hydronium, and because it's gaining an extra positive particle, it has a charge of +1. It becomes a polyatomic ion called hydronium. And then all we have left is the chloride ion that we had before from the hydrogen. So if we look at what's happening here, we can see that the proton from the hydrogen chloride is going to join with the water. So the water is accepting the proton, and the hydrogen chloride is donating the proton. So that means that the hydrogen chloride is the Bronsted-Lowry acid, and that the water is the Bronsted-Lowry base. And that's basically how that works. You have to look at your whole equation that you have. Look at the whole thing here. and try to figure out what's going on. You have to try to think about what you had before and after and how things have changed. So if you look at what you had before compared to what you had after, it's clear that the chloride is by itself and that that hydrogen went somewhere. And where did it go? Well, if you look at what you had before and what you have after has one extra hydrogen, it has one more proton. So you can tell that the proton went from the chloride to the water. Now, when you have questions like this, what you're going to see is what's in the green bubble right here. You're not going to see down here the thinking that I kind of modeled for you. So you're going to have to be able to look at an equation like this in the green bubble and see in your head what I've drawn down here, or write on a piece of paper what I've drawn here, so you can figure out where that hydrogen is going. Okay, I think I'm going to go one more example here, and then we probably are pretty much done. But I did mention that you don't necessarily have to have water for these reactions. So let's just look at one that doesn't have any water in it. You can have, for example, let's just see. You can have, let's do a really crazy one where you wouldn't even really know the names of any of this stuff. So let's say you have this equation right here with C2O4, and that's reacting with HC2H3O2. And when that reacts, it forms HC2O4 and C2H3O2. Now, when you first see this, your eyes it's kind of swell. Your eyes might go kind of crossed because holy cow, look at all this stuff, and I don't know what any of this means, and blah, chemistry. But it's really not that big of a deal because remember, we just care about what's happening with a proton. So we have to try to find in here where a proton has moved from one spot to another. And so I propose that if you compare the reactants to the products, for me, the first thing that jumps out is this right here is basically just an H tacked onto C2O4, which we had by itself over here. Well, remember, H's protons, that's what this is all about. So where did that H come from? Well, the H came from, if we look in the reactants, looks like C2H3O2, which is by itself on this side, was not by itself over here. It actually had an H with it. And so what happened is that this H left the C2H3O2 and it joined up with the C2O4 to make HC2O4. And so the HC2H3O2 donated its proton to the C2O4. And so that means that the C2O4 is the Bronsted-Lowry base, and that the C2H3O2 is the Bronsted-Lowry acid. And that's really all there is to it. You just have to look at which one of the compounds is losing a proton and which one of them is gaining it, and you can pretty easily find out that way which one is the Bronsted-Lowry acid and which one is the Bronsted-Lowry base. Thanks for watching, and as always, if you have any questions, please ask in class. Take care.